Hi, I'm Akul.
I'm Abby.
So over these past 10 weeks, we've been imaging star spots and basically trying to research how they're changing and growing on the surface of this particular star called Pegasi. We call it Peg for short. This star is located more than 80 light years away in the Pegasus constellation. Since this star is really far from us, we can't image the spots directly. Therefore, we use some other indirect techniques. But before we get into all of that, let's give you a brief summary of how spots are formed and what they are.
So a star spot is a cool, dark region on a star's outer layers where powerful magnetic fields have suppressed convection currents within the star. And this occurs as a combination of two phenomena, these being flux freezing and magnetic tension. Flux freezing occurs when you have a very powerful magnetic field that becomes embedded within a conductive substance. And as a good example of how flux freezing occurs, consider a highly conductive wire loop with resistance equal to 0 moving through a magnetic field. Ohm's law tells you that such a loop cannot have any voltage in it, and Faraday's law tells you that if there is no voltage, the magnetic flux has to be constant through it. This can really only be the case if the magnetic field lines passing through the loop are frozen into it so that as the loop moves, the field lines are moving with it. In a star, the highly conductive stellar plasma takes the role of these loops so that the magnetic fields become embedded within the plasma. Then these frozen field lines begin exerting forces on the charged particles within the plasma. This is where magnetic tension arises from. Basically, when these forces become very strong, it can cause the magnetic field to become stiff and tense, resistant to bending, so that if the plasma tries to move it in a way that would distort it, the field will pull back and pull the plasma into line. In a star spot forming region, you have a very powerful vertical magnetic field several thousand times stronger than usual, and because it is frozen to the plasma and exerting these tension forces on it, the plasma has a hard time moving sideways. So the sideways motion of plasma is restricted. This is an important part of the convective process, so when this motion is restricted, convection is also suppressed. Convection being the main mode of heat transport in the star means that this region is no longer receiving as much heat as the rest of the star, and this causes that plasma to cool off, become dark, and that is what we see as a star spot. Since the star spots themselves are darker than their surroundings, we can infer their existence just by seeing how the star's brightness changes as it rotates. So when rotation brings a star spot into view, we can observe the star dimming even though we can't actually observe the spot directly.
And that's essentially what we're trying to study. We're monitoring how the star's brightness is changing as it's rotating. And to do so, what we do is we take images of the star in the surrounding star field using our 14-inch aperture telescope. We call it PERKY. So we take our data through we take our images through this telescope using the 4 standard photometric filters: the blue, visual, red, and infrared. After we take these images, we analyze and calibrate them, and we use one of the indirect techniques that we were talking about. Is called differential photometry. So in differential photometry, what we essentially do is we try to calculate the magnitude of our variable star Peg based on the known magnitude of another star, which we call a comparison star. Doing so, we get the data which shows us how Peg's brightness is changing as it's rotating. And that data is necessary for us to plot our light curves. And that's essentially how we infer their existence without actually having to image them, because as Abby mentioned, as the star rotates and brings the spots into our line of sight, the overall brightness of the star decreases, which we observe as a trough in our light curve. As the star continues to rotate and takes the spots out of the view, the overall brightness increases again, and that's what we observe as peaks in our light curve. Now, what's important to note here, if you look at the data that has been collected from 2014 till date, 2019, not only is there variation in Peg's magnitude on a night-to-night basis, there's also long-term variation from a year-to-year basis. So in 2016, Peg was at its brightest magnitude of 10.3. However, in 2019, it's been recorded to be as low as 10.5. And one of the possible reasons we feel that it's become dimmer is because of the increase in the size of its polar spot, which was inferred through 2003 Doppler imaging. Now, unfortunately, we don't have any recent Doppler imaging of Peg, nor do we have light curves supporting the Doppler images from 2003. So we don't exactly know what's the true size of this polar spot. Therefore, we've somewhat arbitrarily chosen it to be around this year, polar spot. The rest of these sizes are relative to that size, so they're not taken absolute.
So once we finally have our light curve data, the last step is to run it through the light curve inversion algorithm, which was written by our mentor, Dr. Herman, and which we can use to build possible models of the surface of LO-Peg. What this algorithm tries to do is that when given light curve data, it tries to produce a model which, when rotated, reproduces the light curve that we gave it. And that's what we can see presented in this final panel here. Each of these models on the left was made using our light curve inversion algorithm. It includes a relative size for the polar spot that year, as well as a possible distribution of star spots on its surface. And to the right is a graph showing how the model's light curve fits compared to the original data curve.
And in conclusion, one of the main reasons why we study star spots is because it gives us a good idea of what stellar magnetism is and how magnetic cycles operate within other stars. It also helps us get a better understanding of our own sun. Thank you.